All right, today we're going to become detectives. We're taking a deep dive, literally miles beneath the Earth's surface, to see how engineers use something as simple as pressure data to decode the secrets of these massive, hidden oil and gas reservoirs. Let's jump right in.
I mean, that's the big question, isn't it? You've got this enormous formation of rock and fluid, but you can't see it, you can't touch it. So what do? Well, the answer is you learn to listen. You listen very, very carefully to how the reservoir breathes. And it breathes through changes in pressure. This, right here, is why well test analysis is so powerful.
So here's our game plan. First, we're going to crack the reservoir's secret code. Then, we'll look at our three main detective tools, the MDH, Horner, and superposition plots. And finally, we'll see exactly what kind of treasure these clues unlock for us.
Okay, first things first. Every good detective has to understand the language of the evidence they're working with. For us, that means getting a handle on the basic language the reservoir speaks. This is the absolute foundation that makes everything else we're about to do possible.
So, what exactly is semi-log analysis? At its core, it's this incredibly clever mathematical trick. We take what looks like a messy, chaotic stream of pressure data, we plot it on this special type of graph, one with a logarithmic timescale, and we look for one simple, beautiful thing, a straight line. Believe me, that line is everything.
And this right here, this is the secret code. For a very specific period during a well test, a phase called Infinite-Acting Radial Flow takes over. The best way to picture it is like the ripple spreading out perfectly after you drop a pebble into a huge, calm pond. During that special time, the relationship between pressure and the logarithm of time just snaps into a perfect straight line. And the secrets of that line, its slope, its position, that's the treasure we're hunting for.
All right, let's grab our first tool from the kit. This is the Miller-Dias-Hutchinson plot, but pretty much everyone just calls it the MDH plot. Think of this as our most basic first-level clue.
The MDH plot is super straightforward. You just plot pressure against the log of the time that's passed. But, and this is a big but, its use case is incredibly strict. You can only use it for the very first time you ever flow a brand new well. That's it. Its only job is to find that straight line so we can measure its slope.
And here's the catch, the big limitation. The MDH plot has a fatal flaw. It has absolutely no memory. It doesn't know anything about what happened before the test. This means as soon as you shut that well in, or even just change the flow rate, the MDH method is totally useless. We're going to need a smarter tool.
And that smarter tool is the Horner plot. Now this was a huge breakthrough. It was a really clever way to actually account for the well's past, which gives us a much more flexible way to do our analysis.
So the Horner plot is specifically designed for a pressure buildup test, after a period of steady production. It uses this neat mathematical trick to remember how long the well was flowing before it was shut in. And that's what lets it accurately see through the well's recent history.
The real genius of the Horner plot is right here, on its x-axis. You see, where the simple MDH plot only cared about elapsed time, Horner uses this special time ratio. And look, it includes TP. That's the total production time before the test even started. It literally bakes the well's history right into the graph's DNA. That's what makes it so much more powerful.
The Horner plot also has this kind of funny quirk. Because of that special time ratio, the data actually plots backwards. Yeah, the test starts on the right side of the graph with the early data, and then it moves to the left as time goes on. It's a really unique signature of this method.
Oh, and the Horner plot gives us a brand new clue. If you take that straight line and just extend it all the way back, you find this value called P star. Now, this isn't a real pressure you could actually go measure, but it's an incredibly important reference point. It helps us figure out the actual average pressure way out in the reservoir.
Okay, so MDH is for the very first flow. Horner is for a simple buildup after one flow period. But what about real life, where flow rates are changing all the time? For that kind of messiness, we need the master key, the superposition plot.
This table really sums up our journey perfectly, doesn't it? We started with MDH for the absolute simplest case. Then we moved up to Horner for the next level of complexity. And now we're at superposition, the powerhouse method that can handle any flow history you can possibly throw at it.
The superposition plot is the modern industry standard for a very good reason. It's just the most robust and reliable method we have because its math can handle the messy reality of a well's actual life. It seriously does not matter how many times the flow rate has changed, superposition can slice right through all that noise and find that all-important straight line.
So how in the world does it do it? Well, instead of a simple little time function like MDH or Horner, it uses a really complex summation. It literally adds up the pressure effects from every single rate change the well has ever seen. This, by the way, is why we need computers for modern well test analysis. You are not doing this calculation by hand. Trust me.
Okay, so we've gathered our data, we've picked the right tool, we've found our straight line, so what? What's the payoff? What are the prizes we get for all this detective work? Let's talk about what this all really means.
The first, and arguably most important prize, is something called permeability thickness, or just K. This number is the single best measure of a reservoir's flow capacity, of a well's potential. To put it simply, this is the number that tells us if we've got a dud on our hands or an absolute gusher. And we get it directly from the slope of that straight line we work so hard to find.
Prize number 2 is skin. Skin tells us about the condition of the well right around the wellbore. Think of it like this. A positive skin means there's damage, like a clog in a pipe that's restricting flow. That's bad. A negative skin? That's awesome. It means the well has been stimulated and is actually flowing even better than we'd expect.
And our final prize is that P-star value we talked about. Now, even though it's a theoretical pressure, it acts as this absolutely critical anchor point. It's the key that unlocks our ability to calculate the average reservoir pressure, which is what helps us estimate how much oil and gas is actually down there.
So let's put it all together. Here's the detective's workflow, plain and simple. First, you get the data from a well test. Second, you pick the right tool for the job, MDH, Horner, or superposition based on the well's history. Third, you hunt down that straight line clue. And fourth, from that one clue, you calculate the grand prizes, the reservoir's flow capacity and the well's health.
So, if you only remember a few things from all this, make it these. First, that straight line on a semi-log plot is the secret code. It's the key to everything. Second, you've got to pick the right tool for the right situation. And finally, the whole point of this exercise is to find K and S, the ultimate measures of your reservoir's quality and your well's health.
We've just seen how powerful semi-log analysis is for reading a reservoir's past, for understanding its fundamental properties based on how it has behaved. But that leads to an even bigger, more exciting question. How do we take these properties, these static numbers like permeability and skin, and use them to forecast how a well is going to perform for months or even years into the future? Well, that's a whole other mystery for another time.